So what we're going to do is we're going to start by just formally writing down a mathematical model for what happens when I have a continuous signal like this, and I'm just going to keep like a number of samples from this signal. Okay, so I'm going to grab a sample, I don't know, here, and here, and here. What happens when I do that, and how do I actually model that mathematically? So the mathematical model, and like I say, I think you've seen it before, is that we're going to think of this process as a multiplication with an impulse train. Okay, so we're going to take the signal, and in the time domain, we're going to think about it like this, that we multiply this thing with an impulse train. And the impulse train will have pulses, little impulses, every t seconds. Okay, so at minus t, okay, actually at minus 2t, up to, like, it starts at minus infinity. From minus infinity, minus 2t, minus t. At 0, it has a little impulse. At t, it has an impulse. So at 20 milliseconds, at 40 milliseconds, and so on, 2t. Okay. Now, the result of that multiplication is another signal, okay, in the time domain. It kind of looks like our original signal. Okay, so here's our original signal, dot, 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 down, and then big wave, and then down, chunk, okay? And now I've multiplied, so I multiplied this thing with this thing, and the result of that is just a bunch of impulses, okay? The first impulse will be at time t, let's say it's there, so there's a little impulse at t, at 2t there's an impulse, at 3t there's an impulse, and so on. And the heights of these impulses, that would just be like, this would just be like whatever x is at 3t. This would just be x at 2t. Someone asked an excellent question after my first lecture, and they said, the student asked, how can you say that this impulse has an amplitude of whatever, this thing here? Or this one, how can you say it has an amplitude of this thing? Impulse isn't actually defined at the point where it happens, right? It's just this thing that integrates to 1. Or if I multiply it with some scalar, then it integrates to that scalar. So what's the answer to that student's question? That's right. That's spot on. So even though we sometimes do this thing where we think of this as the amplitude at that signal at that time point, or the amplitude, it's a fine way to think about it. But really just remind yourself, it's not really an amplitude. It's just the strength of the signal. It's the value I get when I integrate over this little thing. So if I integrate like this little impulsy thing here over that portion, then I get a value of x at 2t. Everyone happy? Okay, so it's a strength. It's not an amplitude, but very often we just draw it as a little amplitude, and that's fine. That's it. And then the last part of this mathematical model that we do is we can't store impulses, right? We can't store these infinite things on a computer. So what we actually store is the strengths of the impulses. That's the last step. So this is this little block here. This is x sample t. So it's this signal at this point here is the one with the impulses. And then we have a little block which just said, convert the impulse train or the impulse strengths to a discrete time sequence, because we can store discrete numbers on a computer. So that's when we get our final signal out like this, and really that final signal would just be 0, and then some negative value here, and then some positive value here, and some positive value here. And this is like x1, this is x2, and this is x3. And these are just the strengths of those impulses at those different points in time. Okay, this is at n, and this is xn. So we have a little, this little block here, which is convert impulse strengths, convert that into a list of numbers. And now I've got a game to play, because I can load my list of numbers into Python and I can process it, and I'm very happy with life, and there's butterflies and everyone likes each other. Okay, But it's important that here you end up with a little list of numbers, okay? And that's a discrete signal that you can process. Everyone happy on the inside? Now, the crucial question is, what happens in the frequency domain when I go through this process? Okay, so here's the frequency of my original signal. This is a little made-up signal, right? So let's just go through the steps. Okay, I'm going to multiply. I've multiplied in the time domain. What happens in the frequency domain? Convolution. Thank you. Okay, and I'm convolving with, in the frequency domain, I'm convolving with what? So in the time domain, I'll multiply with the impulse train. In the frequency domain, I convolve with a what? Another impulse train. Well done. Okay, and that thing has impulses from minus infinity up to some point here, and then another impulse here, and then another impulse here, and another impulse here. Can you remember where these impulses sit? If this is at t, where does this one sit and this one sit? 1 over t. Wonderful. Thank you. So this one is at 1 over t, and this one is at 2 over t. And that makes sense. In the frequency domain, we know that if things get squashed in the time domain, then things spread out in the frequency domain. It always happens. Okay. So that's exactly right. Okay. So when I convolve this thing with this thing, what do I get out? That's exactly right. So basically, this little thing here, it gets copied at 0, and it gets copied at minus 1 over t, and at minus 2 over t, and at 1 over t, and at 2 over t. Okay. And so you get this little chunk, and at 1 over t you get a chunk, and at 2 over t you get a chunk, and there's one at minus 1 over t. Okay, and this is the frequency content of my sampled signal. You can think of that as the spectrum of this thing. Okay, we'll get into the details there about exactly how you think of the spectrum of a discrete time signal in quite a lot of detail just in a little bit. Awesome.